All right, so today what we really basically need to cover, we're almost finished up with triglycerides, but we need to talk about the three reactions that triglycerides undergo, and then move on into phosphoglycerides and look at how they are similar to triglycerides, but also how they are different. What are the similarities and differences of phosphoglycerides with triglycerides? And then we'll move into sphingolipids, and then finally steroids. And look at the cell membrane and finish chapter 17. All right, so we got this far, and we mentioned that triglycerides are mixed triglycerides, meaning that although they have 3 fatty acids on them, usually in nature, naturally found triglycerides are 3 different fatty acids. And you can see that right here with olive oil. There's going to be some oleic acid, there's going to be some stearic acid, there's going to be some other fatty acid on the triglyceride. Beef fat, there is some oleic acid, not as much. There is some stearic acid, a lot more. And there is some other fatty acids. So there's 3 different fatty acids there. So that's what we mean by a mixed triglyceride. So you can actually go in and look at coconut oil or any other oil you want and see what fatty acids make those up. All right, this slide introduces the 3 different reactions that triglycerides can undergo. And this one we would call hydrolysis. This one, when you have a ester react with sodium hydroxide, what do we call that reaction? Saponification. That's the opposite of esterification. Saponification. You're reacting an ester with a strong base. And when you react an unsaturated or a double bond with hydrogen, what do we call it? Yeah, hydrogenation or hydrogenation, however you want to pronounce it. It actually has hydrogen in its name. Hydrolysis, you're reacting something with water. All right, and this is actually why these triglycerides get the name or are put in the class of saponifiable lipids. This is a saponifiable lipid. It can undergo saponification. All right, so the next 3 slides just give an example of those 3 reactions. Here's the first one, hydrolysis. We're reacting it with water. We have our triglyceride. It's a triester. React it with water in the presence of an acid. And we get glycerol and the 3 fatty acids. So when you see the triglyceride, I may be talking too fast here. When you see the triglyceride and I say there's a fatty acid, it's not in the form of the fatty acid. It's been esterified to the glycerol. You have an ester linkage to the glycerol. You react it with water, you're inserting a hydrogen here, and you're inserting an OH there, and generating the fatty acid and the glycerol. You're breaking it down. That's hydrolysis of the triglyceride. Now let me just point out this little word right there. This is a kind of a prelude or preview of chapter 19. That is an enzyme. And when you see the OSE ending, you think of a saccharide, sucrose, etc. When you see the ASE ending, you will be thinking of an enzyme. And look at that enzyme, lipase. What is that enzyme? It's a catalyst for a biological reaction of what? The breakdown of a lipid, lipase. So sometimes there is a hint in the name of the enzyme as to how that enzyme functions. This is lipase. So in the laboratory, I could take olive oil and a little bit of an acid of some sort and water and break it down into this. Just kind of doing a wet chemistry experiment or a reaction in the laboratory. In the body, if the body has a triglyceride and actually does want glycerol for some reason, or does want to use the fatty acid for some reason, or wants to metabolize that fatty acid, actually wants to burn it, it may start with lipase and break it down into its components and then process it from there. All right, so yeah, so that's hydrolysis. Now here's saponification. This is a reaction that's going to be taking place outside of the body. So this isn't necessarily what the body is doing. But if you wanted to use olive oil to make soap, this would be the way to do it. And notice you got 3 NaOHs because you have 3 esters here. You're going to get glycerol just like with hydrolysis. But instead of the fatty acid, you're getting the sodium salt of the fatty acid. So these are soap molecules. Hydrophilic head on them, negative, positive ions, very hydrophilic, hydrophobic tail, and that's the ingredient for a soap forming molecule. So that's saponification. Sodium hydroxide, you're going to make hard soaps. Liquid soaps, oftentimes we'll use potassium hydroxide to make a liquid soap formula.
I have a question.
Yes.
On the tester, are we going to have to draw out like the triglyceride and then what it forms, like each thing, like that whole thing? Or is it more like what is it going to form sort of thing?
Good question. Has to do with the test.
Dustin also likes it when someone else asks some of these questions.
Go for it.
He likes it. Yeah, he says go for it. Because he knows my standard answer. Well, the triglyceride is, on this chapter, there's tons of molecules. I don't expect you to know how to draw all those molecules. Probably the triglyceride is the one that I do expect you to know in as more detail than anything else. What a fatty acid is and what a triglyceride is and what it looks like. Now, I wouldn't expect you to draw a complicated triglyceride like that. I might say, draw one that has 3 stearic acids on it. Okay? It's got 3 stearates. So it's a pretty, not a bland one, but a pretty homogeneous one. And it's got the same fatty acid all 3 times. All right? I don't expect you to go into that kind of detail. But, so, well, let's just draw that. So let's say we had this, we have a stearate, we have, not stearate, we have a glycerol backbone here. And it's going to have an ester link. The fatty acid is going to be, what was a fatty acid is going to be linked to this through a stearic acid bond.
So that's always the case
in a triglyceride, yes. All 3 of them are going to be linked like this. And then if this were stearate, remember stearic acid has how many carbons in it? 18. So it's going to have a bunch of these, and on the end it's going to have one of those. Right? Yes? So how many of those is it going to have? 16. And if I said draw one that's 3 stearic acids,
So we don't have to draw out would you want us to draw each of those out, or can we just write it just like that?
you could write it just like that.
Yeah, I'll let you know that. We're on the way up to it.
I don't know what I'm going to do without him. I'll answer that. Oh, Dustin, you've pushed us right to the boundary, but that's good. I like it. I like confidence. Okay, so there's a triglyceride, and then you should, you should be able to kind of go on here and react that with 3 water molecules and break it up into, I already told you, you should have a 3x5 card on this molecule, right, Dustin?
Right.
This is glycerol, and on the final exam, I could say, draw glycerol. It could be one of the things that's right there. On the final exam, there will be 10 or 12 things that are just that. Glycerol, acetic acid, formaldehyde, whatever are these molecules that I've said you need to know the structures of, and there'll be about 12 of them. And you got to draw them.
Okay, so it's a triglyceride because of the 3 esters?
Yeah, triglyceride. Where's it getting the glyceride name? From glycerol. It is a triglyceride. Yeah. It's got 3 fatty acids attached to this glycerol molecule. Guys, walk down HEB, get the labels, look at them. What you'll see on some labels, you'll see partially hydrogenated vegetable oils. That's those triglycerides. You will see mono and diglycerides. Mono and diglycerides. What have they done? They've taken a triglyceride and they've clipped one of these things off of there. And I don't exactly know why they do this, but they have done that, and they have in their mono and diglycerides. Mono, a diglyceride, they've clipped one off. A monoglyceride, they've clipped 2 of them off, and they've left the glycerol molecule with a fatty acid on there. And they're doing it for some reason. I don't know how it emulsifies the ingredients in there, or whether it's got to do with melting points. Rick?
Yeah, so I see where the OHs go from the 3 water molecules, but where's the other H go, in the product side?
Okay, so let's put an H right there, and let's put an OH right there. There's your water. You follow me, Rick?
Yeah, I think so.
Yeah. So there's your OH, and now you also need to make this into a carboxylic acid.
So the left part of that becomes the glycerol, and then
The right part of it becomes 3 fatty acids.
okay, there we go. I got it.
Yeah, the right part becomes 3 fatty acids.
So your oxygen becomes an OH, right? Is that what you're saying?
Your water. See, we're inserting a water molecule in here.
Right. So that becomes an OH, and then what?
He wants to know where the water goes.
Yeah, well,
So it becomes.
so let's do this one down here. Here we got an O. Okay, we got that, right?
Okay.
So we come along here with the water molecule.
We're losing the double bond, right?
No,
So a double bond.
no, that stays there because this fatty acid looks like this on the end. Okay? I mean, it's so the water molecule is, that bond is breaking, and the water molecule is breaking up into part of it going, I think, yeah.
They're no longer connected, is that what?
Yeah, they're no longer connected.
Okay.
Look, let's go back here. Look at here. They're no longer connected. This is written, let's go back to hydrolysis. Let's go back to hydrolysis. See, this is separate. This is all by itself. And here's your carboxyl group. And so where did the water come from? That and that.
Gotcha.
Do another example.
Instead of just connect, like what?
Well, that's the only example I would expect you to do, is where it's 3 stearates. Well, let's, okay, here's what we can do. We can simplify it a little bit. You got this molecule. I think maybe what's confusing you here, or a little bit hard to follow, is it's so complicated down here. So let's just focus on one of these. So we add water to this. We add water to this bond right here. And so don't worry about this other part of this molecule right now. Just, so we're adding water, and what is water? H2O is HOH. That's H2O. Part of it is an H, the other part of it is an OH. And so okay, so this happens 3 times, okay?
So you're just taking that bond away.
Yeah, we're taking that bond away. And it is
I'm just going to repeat that same thing for the next 2.
right.
Can you just keep explaining, please?
You would repeat that. What?
Got it. Okay. Yes, can you keep explaining it?
Yeah, well, you're breaking that bond, and water is going to part of it. We broke this bond here. And the H is going to here, and the OH is going over here, and there's nothing here now. These are 2 separate molecules floating around. And then if you had this right down here, then the same thing happens to that one. If you had this right down here, the same thing happens to that one. And you get your glycerol, and you get 3 of these. So, yeah.
And this was hydrolysis?
This is hydrolysis. Okay. So this is saponification. All right, so a good little exercise for you on the side would be to start out with that molecule I had there with 3 stearic acids on it. Start out with this one that has 3 stearic acids on it, and use 3 sodium hydroxides and break it back down into glycerol. And what you're going to get glycerol and 3 stearates, sodium stearates. What is sodium stearate? It's going to be, well, if we draw it the same way it's drawn here, that's sodium stearate. But you'll get 3 of those and 1 glycerol. So in both saponification and hydrolysis, you get glycerol. You just get a little bit different thing here. You get the sodium salt of the fatty acid. When you saponify it, you get the fatty acid when you do hydrolysis. Okay. Hydrogenation. We're reacting with hydrogen. Now this one's a little bit confusing because there are 3 double bonds in here to begin with. Let me try to, I'm just blowing this up. Here's oleic acid right here. This is oleic or oleate because it's bonded here. But there's a double bond. You see there's 7 CH2s, the double bond, 7 CH2, CH3. Remember I told you the double bond's right in the middle of the molecule like our elbow? You come down here, this is linoleic, I think, linoleic acid. But notice there's a parenthesis right here. Parentheses right here. Parentheses, and there's a number 2 right there. So what does that mean? We got a double bond here. CH2, CH, double bond, CH, and they're saying there's another one of these, a CH2, CH, double bond, CH. So there's 2 double bonds in this fatty acid, and 1 here. Now what does hydrogen do? Hydrogen hydrogenates a double bond. One hydrogen will eliminate 1 double bond. 2 hydrogens will eliminate 2 double bonds. But there are 3 double bonds. 1, 2, 3. So we hydrogenate it with a nickel catalyst. No double bond here. We've converted to CH2, CH2, CH2. This CH2, CH2, CH2. Because we got rid of the double bond by adding hydrogen to it. But that one is still there. So this is a case where you are partially hydrogenating it. Partially hydrogenated. What does that mean? We haven't eliminated all the double bonds. And you will find that, again, in HEB. Wander down through there. When you're bored sometime, wander down through there and read the labels. Just pick stuff off there. Peanut butter, ketchup, mayonnaise, whatever. If it's not organic or natural or non-GMO or whatever, it's going to have been processed. It might say partially hydrogenated vegetable oils.
Is that the case for every
Peanut butter?
No. Well, I don't know.
Well, okay, Alyssa, typically when they are hydrogenating things, they're trying to get a certain melting point. Okay? And remember I showed you how double bonds affect the melting points. So they know if they completely eliminate all the double bonds, it's going to be real hard. You're going to take that margarine, get your toast out, and put it on your bread, and it doesn't melt. It just sits there, big chunk of margarine. And people say, I don't want to buy that. I want it to spread. So they're going after a certain melting point that will melt just on the toast, right out of the toaster. Shwink. Ah, I love it.
So for some products.
Yeah, for some products. They're shooting for a certain melting point or certain characteristics, so they don't fully hydrogenate it. But this is what gives rise to trans fats. Is somebody doing an article on trans fats? Is there a project on trans fats? Aaron? Okay. So I'm going to let Aaron tell you all about it. Tomorrow, Wednesday. No, soon.
After Thanksgiving.
After Thanksgiving. Yeah, we don't want to spoil our recipes.
So is this what they're doing with that liquid coconut oils in? Partially hydrogenated?
No, that's just that's medium chain triglycerides. Because the chain length is gone down, it's a liquid. They're just extracting it out of coconut oil.
Okay.
If you melted coconut oil and then let it start solidifying, the last stuff to solidify would be the medium chains.
Okay.
So you could probably skim that off and extract it that way. Yeah, so they're going to have a much lower melting point because there's shorter chains. Okay, so this is partially hydrogenated. This is hydrogenation. Crisco. So the implications is it can produce some trans fats because those catalysts in there can isomerize the double bond. It's all cis to begin with. You throw a nickel catalyst in there and you don't have the hydrogen to react with the double bond, the nickel will associate with that double bond and make it flip around, and you'll get a mixture, cis and trans, coming out of there. Okay, just 30 seconds on waxes. Beeswax and also the wax that accumulates in your ears is a wax. And what is a wax? Notice what you have here. You've got 15 carbons. So let's do that. So there are 15 carbons here, and there are 30 carbons over here. So 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. You got that? And then you got 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. There's a wax. You got one ester bond there. So you don't have glyceride here. This isn't a glyceride or a triglyceride. That is a fatty acid. And this is a long chain alcohol. So what did you have here? You had an alcohol reacting with a fatty acid. You split out that water molecule and you get an ester linkage. Nonpolar, very nonpolar tail here. 30 carbons long. Nonpolar tail over here. Okay, beeswax, a beehive sitting out in the rain for 30 days doesn't dissolve. The water isn't soluble in beeswax. Zilch solubility. All right? So hire the bees, tell them to put beeswax on your roof. Do a good job. You don't need shingles. All right?
Just ants.
Just ants. All right? Of course, you're going to get a lot of stings, but other than that. But this is very nonpolar, very hydrophobic, very insoluble in water. Yeah. That's wax. And where does it show up? Basically in bees' hives and in your ears. Okay. Now, let's go on to phosphoglycerides. Let me just compare and contrast here for a second. We've just come from triglycerides. This is your triglyceride, which we just studied. And here's your phosphoglyceride. You don't need to draw these in any really great detail. I expect you to appreciate the similarity and the difference between triglycerides and phosphoglycerides. Similarity: glycerol backbone, fatty acids. Difference: this one, just 3 fatty acids. This one has 2 fatty acids and a phosphate ester portion of it. And so we'll dig into that. Why are these important? We'll end the chapter looking at the cell membrane and what the cell membrane looks like and why it looks that way and why it functions the way it does. This is the primary component of the cell membranes of your body, phosphoglycerides. So this would be one headliner for why you need some fat in your diet, because it is lipids that is protecting every cell of your body. So you do need some fat. Your body's either going to have to make it, and it can't make all of it, or it's got to get it in the diet. So phosphoglycerides. And they're going to differ. There's going to be, this is a class of molecules. You put a different alcohol on here, and you have a different phosphoglyceride. Let's go over to this slide. This is a better slide. So there's your glycerol backbone, fatty acid, and again they can be different. Phosphate ester linkage. What does that look like? Down here, yeah, I think it would be wise to be able to know this little portion of this phosphoglyceride. You got a phosphate bound to that glycerol backbone. Here's your fatty acids on here. Got this phosphate group, and then you have, here's where the variety comes in. What is X? Define X, and you've defined a certain phosphoglyceride. If X is this molecule right here, so if this is X, choline, you got 2 carbons, and then look at here, you have a quaternary ammonium cation, a nitrogen with 3 methyl groups on it. That's a quaternary ammonium cation, so that those are naturally occurring molecules in nature, and that would be an X. Serine is an amino acid. It's an alcohol functional amino acid. So you're bonding it on right here.
So that X replaces that H on there, on that left side? Is that where that would go?
The OH. Okay, because this O is going to be that O. Okay, there's not going to be 2 O's next to each other.
Okay.
So your phosphorus would be right here. All right? It'd be linked phosphorus, oxygen, choline.
Okay. That makes sense.
All right? Because what you would have had there, you would have had this here, and your alcohol here, and you're splitting out water, and you're forming a phosphorus oxygen carbon bond. All right, so if it is, so PG is referring to phosphoglyceride, PG, on these slides. We're just kind of abbreviating it to a PG, phosphoglyceride. If it is choline, it would be called phosphatidylcholine. You don't need to get into this level of nomenclature, but just to kind of be familiar, phosphatidylcholine is a phosphoglyceride. It's also called lecithin. So if you get into anatomy or into the endocrine system and you hear some of these words, they are particular molecules. Cephalins are in the blood platelets. This is a serine. Yeah, there, Stephen. You can see the phosphorus oxygen carbon bond right there, where the serine is bonded to the phosphorus with an oxygen between them. All right, that's phosphoglycerides. We'll come back when we look at the cell membrane, and you'll see how they are instrumental in cell membranes. I'm going to have a slide here on sphingolipids, which could also more or less apply to these phosphoglycerides in a second. All right, when I said phosphoglycerides are essential to the cell membranes, most of the cells in your body. Sphingolipids are particularly the molecules used for the cell membranes of your nerve cells. So nerve cells have a particular lipid that is the major component of their cell membranes, and that's this, sphingolipids. These are not saponifiable lipids. Or wait a minute, maybe they are. Yeah, I guess maybe they are. Hang on a second. Let's go back here. Lipids. Oh, sphingolipids, yeah. Okay, so they are kind of saponifiable, not in the same exact sense that these are, but they are saponifiable. Oh, I should have seen what slide I was on. Sorry, I got to jump around here to find out where I was. Okay, sphingolipids. Instead of glycerol as the backbone, sphingosine is the backbone. All right, you can see 3 carbons here. 1, 2, 3, like glycerol, but not glycerol. There is an OH on that one. There is an OH on that one. There is an amine on this one. This is sphingosine. There are 1, 2, 3, plus 12, 15 carbons here. So this is a long nonpolar tail. This is the backbone. Now, this right here is this purple. Okay, the purple section here is basically this sphingosine. So what is a sphingolipid? Well, take sphingosine, add a fatty acid right here at this point. Notice that that's not an ester, it's an amide link. And then down here you're going to have a phosphate group and an X. So it's kind of like a phosphoglyceride, but not like it. It's different. Well, here's how they are similar. You could make this same sort of drawing for both the sphingolipid and the phosphoglyceride. You've got a phosphate group with an alcohol on it. You got a head on your phosphoglyceride or your sphingolipid that is polar, and you have a fatty acid and 2 nonpolar tails. Okay, on sphingolipids, one of the tails is this long carbon chain and a fatty acid. On sphingolipids, they're both fatty acids. All right, so there's your 2 nonpolar tails and a polar hydrophilic head. All right, when we get to cell membranes, you're going to see how these molecules form this lipid bilayer to form the cell membrane. Yes?
So it still has 3 fatty acids?
2. Only 2. Okay, both the sphingolipid and the phosphoglyceride only has 2 fatty acids or long chains on there that are nonpolar. So that's where they differ from the triglycerides. But they got this phosphate group. Look at that, lots of oxygens, a negative charge. They're just, and then they got these alcohols on them with charge on them. So a very polar head, very water-loving head, and 2 hydrophobic tails. Sphingolipids. All right, so sphingomyelin or the myelin sheath. What's the myelin sheath? It protects? Okay, the axons and neurons. It's a cell membrane around them. So you got nerve cells with these real long tendricles coming out of them, right? And it needs to be protected. So nerve cells have lots of cell membrane. Lots. They're long, these long tendricles coming out of them, neurons and axons and all that other Star Wars nomenclature. All right? And yet they have a sheath around them. The myelin sheath. So that's sphingolipids. You can start adding some sugar molecules on the sphingosine and get other kinds of sphingolipids. There's the O antigen blood type right there with a number of sugars coming off of it. You see the sphingosine, the fatty acid, and this 5 sugars. Defining the X, you could get different classes of sphingolipids. And then we were talking about genetic diseases. Here are 4 of them right here, where an individual cannot synthesize these enzymes, and they give rise to these 4 different diseases. I don't know, but I would assume that when you test a newborn, that they're testing for these kind of things, deficiencies in these things. Can they metabolize or can they synthesize these enzymes? All right, so let's go on to steroids. Okay, find a blank spot in your notebook. Start on the left. I want you to draw what I draw. I'm going to draw this on the board. So draw exactly what I draw. There's a 6-membered ring. Draw a nice 6-membered ring. All right, now I'm going to draw another 6-membered ring. I'm going to start right here and draw another 6-membered ring right on the side of it. Ready that far? Okay, now notice what I do now. I'm right here. I'm going to move on up into this. I'm moving up to the right, and I'm going to draw another 6-membered ring coming right off of that position. Right there.
Now I got to erase because it's over.
Is it too much gray?
All right, we're almost there. I should have said use pencil. Did you use pencil? Yes. Okay, now we're going to draw another ring, but it's not 6-membered. We're going to draw a 5-membered ring right here, right on the side of that third one we drew. Draw a house. And what you've got right there is what I will refer to, what we will call the steroid nucleus. Steroid nucleus. So now we're segueing into steroids. So let me just draw it here for those watching at home. Don't touch that dial. little lopsided house, but that's a steroid nucleus. I may not ask you to draw a particular steroid molecule, but I very well could, probably will, ask you to draw the steroid nucleus. So this is what we drew in that particular arrangement of rings. Now notice that these two, let's look at these two rings right here. These two carbons are in both of those rings. So as I say, that's a 6-membered ring, that's a 6-membered ring, that's not 12 carbons. It's only 10 carbons. Because these two rings are they're actually what fuse those two rings together. That's what we would call fused rings. They're not falling apart. This carbon is going over to that carbon and it's bonded to that carbon too. So they're physically bonded together. And that's the steroid nucleus. The main reason this is here, this is kind of the precursor. This would be the molecule that the organism would use to build that structure, this isoprene. You got these double bonds in here and it can start kind of bonding, piecing these isoprenes. So here's your little Lego pieces, and this is what it's building out of the Legos. All right, so cholesterol. Cholesterol, you can see the steroid nucleus here with things coming off of that nucleus. Cholesterol is a steroid. And a very important steroid. You'll see, let's see here on the next slide, I think. Yeah, notice cholesterol here. Now this would be more or less a metabolic pathway, and where there are metabolic pathways, each step requires an enzyme. And each one of those steps would probably have a different enzyme. You know, there's a different enzyme. What is an enzyme? It's a protein molecule. So there's a certain protein that would take cholesterol, rearrange it into pregnenolone, into progesterone, into testosterone, into estradiol. I mean, this is really fascinating. Here's your female hormone, male hormone, and another female hormone. You know, where is the metabolic pathway? Well, to get to this, you actually have to make testosterone and estradiol. So they test a woman's blood and they find, well, there's progesterone. Yeah, there's some testosterone in there. Well, you know, there's probably predominantly that with some of that, but that is possibly on its way to be estradiol. All right, these steroids here are regulating the retention of certain ions. That's what the mineral corticoids, what are they talking about? Minerals like sodium, potassium, calcium, magnesium. You've got these steroids operating in the kidneys that are regulating whether to allow that sodium to pass through the kidneys or to retain that sodium. I think estrogen is tied up in calcium and bone structure and things like that, so estrogen has a role to play in that as well.
Do we need a metabolic pathway?
That metabolic pathway? No. No, what I would expect you to know on the test is questions like, which of the following is a steroid? Okay? And if I could put whatever, glucose, phosphoglyceride, whatever, 5 choices, and one of them would be a steroid. The trick question would be where none of them are a steroid. And I don't have none of the above. That's a bummer question. That's one I end up having to throw out because I didn't have the right answer. Okay, but yeah, so you should know what class of lipid these things fall into as we're studying these different classes. And then I'm not an expert on performance-enhancing steroids, but those are generally modified versions of these molecules. All right? So to find an athlete with a steroid in his bloodstream is not going to disqualify him. Is it a naturally occurring steroid? Is the question. All right, so this gets into exactly what some of those look like. So there's estradiol and testosterone. You can see a lot of similarities. The estradiol, interestingly enough, this is aromatic. That's not a requirement here for this steroid nucleus. It can have, you can see testosterone has a double bond right here. Estradiol has alternating double bonds, so it actually is an aromatic ring with these other three rings. And then, how do I get back here? Notice here, vitamin D3 is saying it's a steroid. You can't really see the steroid nucleus real well, but I think you can imagine, follow me here, if we were to break that bond right there, if we were to take that bond away, all right, and you basically, you're coming down here, 1, 2 carbons, and you're to the next ring. 1, 2 carbons, and you're to the next ring. So on vitamin D3, you basically have the components of a steroid nucleus with that bond broken in it. And it is considered a steroid, even though the nucleus is not entirely intact. So you follow that?
Sure.
Okay. Yeah, no, you don't need to make 3x5 cards of all these steroids and know exactly their structure. I don't. I would look them up. That's kind of the part of my thinking. If this is what I had done my thesis on, I probably said, yeah, you got to have 3x5 cards on this. But I don't know the various idiosyncrasies of all these different steroids. Do know the steroid nucleus and which of these are steroids. Okay, final topic here is cell structure. And what to point out here, we've got prokaryotic or single-celled organisms. Here's where a chemist is trying to venture into biology. Single-celled organisms, eukaryotic, multi-celled. And why is this important? As we go into cell membranes, the thing to point out here, most antibiotics, the kind of the broad range antibiotics, are made to attack bacteria. And you take this and they kill them, kill the bacteria. So you swallow this antibiotic, and let's say you have an intestinal bug or something like that, you swallow the antibiotic, it's going to kill that bacteria in your system, but it's not going to kill your cells. You don't want to take something that's going to be harmful to every cell of your body. And so this is where these antibiotics are targeting. They're targeting the cell membranes of single-celled organisms. And what are they trying to do? They're trying to compromise that cell membrane, break it open, because if they do break it open, it will kill the cell. But that's also why when you take an antibiotic, it kills all the bacteria in your intestines, the good bacteria and the bad bacteria. because it is targeting the cell membranes of those kinds of organisms. So you need to replenish your good bacteria with probiotics. But let's take a peek at the cell membrane and how does it do this? What is a cell membrane? This is a simplistic drawing of it. The major thing is a lipid bilayer. It is a lipid bilayer. So these are phosphoglycerides. And so you've got your hydrophilic head, and you've got your hydrophobic or non-polar hydrophobic tails. Non-polar tails. On phosphoglycerides, those are 2 fatty acids. All right? They don't like water. These don't like water. So what do? They create their own hydrophobic environment, non-polar environment here by the tails pointing towards each other. And so you have water or an aqueous phase outside the cell. You have an aqueous phase inside the cell. But what do you have between it? You have a hydrophobic environment blocking the stuff that's outside the cell from coming into the inside of the cell. All right, so that's for the general cells of your body, this would be phosphoglycerides. For the nerve cells, these would be sphingolipids. But they would look basically the same way. You would have a polar head and 2 nonpolar tails coming off of a sphingolipid. So same concept, just a different lipid that's performing this lipid bilayer. Okay, now that like I said, that's a simplistic view of it. Gets more complicated. There's your lipid bilayer. The blue is the lipid bilayer. And what is in the lipid bilayer? These are protein molecules, huge, complex protein molecules, specialized. For example, this one right here could be an example, that would be an example of a sodium-potassium channel. So for example, a sodium-potassium channel. So there is a tunnel there to allow sodium and potassium ions to get in and out of the cell. Or a calcium magnesium channel. That would be a different protein. It'd be a different protein there. That's a calcium magnesium channel. Or a glucose channel. It'd be a channel like that allows glucose to come in and out of the cell. Notice where these are. Calcium, magnesium, plus 2 ions. Barium nitrate is toxic to the body. Why? It blocks the calcium magnesium channel. So if you ingest something that has barium in it and it gets into through your intestines into your bloodstream, it then plugs up the calcium magnesium channels in your cells and is very toxic, can be fatal by blocking the transport of calcium and magnesium in and out of cells. So this is how this stuff works. We're talking about active transport. So this isn't just a tunnel like where a car gets to the tunnel and goes through the tunnel. This is where a sodium ion gets there and the body decides whether to bring it through that channel or not bring it through. Depends on how much sodium is in the cell and whether it has a need for that sodium. So that's active transport. It's not just the fusion of stuff across here. It's being actively, decidedly moved in and out of the cell based on what the cell thinks it needs. Okay, so there's other stuff embedded in here. There's cholesterol embedded in here, different things. There are, when you say something doesn't accept, like when there's a transplant, there can be things on the surface of these cells that are signals as to whether they like or don't like something that's coming along. Okay, so the cell membrane is about 60% lipid, 40% protein. All right, so and the lipid is either phosphoglyceride or sphingolipid. All right, and I think we've covered these other ones here. Any questions? All right, I said early. If we don't get out of here, we won't keep that promise. So I'll see you when.